Hello everybody and welcome to lesson 3 of similarity. The last two lessons we talked about what it means for two shapes to be similar, and you used the idea that two shapes were similar to figure out some side lengths. In this lesson we're going to kind of flip that on its head and work backwards. I know that sounds fun. And instead of starting with knowing the triangles are similar and saying, okay, since they're similar, I know all the angles are the same, and I know that I have proportional sides, or I know I have that common scale factor. Now the question is going to be, are they similar? So we want to be able to look at them, pull the information from them, and determine, well, it's enough to be sure that they're similar. So this should sound pretty familiar because we did this with congruency, right? When we were looking at whether or not triangles were congruent, we know that congruent means same size, same shape. And we had 4 theorems that allowed us to prove it. So remember, with triangles, there's always three side pairs and 3 angle pairs. And so we said for congruency, you don't need to prove all 6 pairs are congruent. You only need 3, but it had to be a special combination of 3. And it had to be one of these 4 combinations here, right? You could have all 3 sides congruent. You could have 2 sides and the included angle, or you could have 2 angles and either the included side or a non-included side. Didn't matter. Okay, we're going the same way with similarity here. These theorems are going to be very, very familiar. In fact, they're just like these. Same shape, different size, so different theorems. We need less to prove similarity. Right? Similarity isn't as fancy as congruency, I guess. So we only have 3 theorems, and we need a little bit less information. The key thing to note here is we're not necessarily looking for equal or congruence. Right? When it comes to angles, we know our similar triangles should have the same angles. But when it comes to sides, we're not going to be looking for congruency. We're going to be looking at that scale factor and trying to figure out, okay, from here to here, did I use the same scale factor on all the sides? All right, so let's take a look at these theorems. I put a note outline thing in your assignment. So if you didn't see that, if you want to print that to kind of use to do a note outline, it has space for you to write all of the theorems and the examples, and then it has printed out the examples that we're about to do in this PowerPoint. So if you're able to print that and you'd like to, you might want to pause this and go do that. You don't need to print it. You could just write some stuff down. But before you ask, Ms. Britton, should I write this down? The answer is yes. Yes, you should. Because there's 3 theorems and you need to know how to use them so that you can go do the assignment on similarity. And after this lesson, it's going to be quiz time on similarity. So yeah, get ready for that. All right. Here we go. Triangle similarity, 3 theorems. The first theorem is called the angle-angle similarity theorem. Now, technically, we know that if you know 2 angles, you know the third. All the angles in a triangle add up to 180. So if we know 2 angles, technically we know the third. So I suppose we could call this angle-angle-angle similarity, but that's too much. We'll just use angle-angle. Okay, so 2 corresponding angles, so in other words, 2 angle pairs are congruent. That's enough to prove similarity. Because if you know the angles are the same, then you know they have to be the same shape. Okay, so here are a few examples. Let's take a look at this top one. I have an angle here marked 75, and I have its partner over here, 75. That's one angle pair. I have a 31-degree angle here. I have a 31-degree angle here. There's my second angle pair. So these are similar by angle-angle similarity. Okay, this second example is different for 2 reasons. Number one, they didn't give us angle measures. They just marked a congruency. But the other thing to note here is they're doing the same thing that they did to us in congruency, and they're starting to throw those like the hidden congruencies at us. Remember shared sides and shared angles and vertical angles and all that stuff? We're going to see that here. So notice they marked a pair here, right? They marked V and Y. But in the middle here, they didn't mark them, but we know that these 2 angles are congruent as well because we have vertical angles. So they marked a pair of angles and we have a vertical pair of angles. So again, we have angle-angle similarity. Okay. Angle-angle similarity, there's not much to it other than two angles. So if you don't see two angles marked, make sure you look for stuff like a shared angle or a vertical angle. All right, the second theorem is side-side-side similarity. So again, this is the same. Notice the only difference between this and the congruency one is this little baby symbol here that means similar. So if you just write side, 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 that means it's the congruency theorem, that you have three side pairs that are equal. If you write side, 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 tilde, that means these are similar by side, 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 the theorem. So in other words, we're saying I know these triangles are similar, and it's because I checked all three side ratios. Okay, and the theorem is this, that we should have three pairs of corresponding sides, right? And their ratios should all be the same. So in other words, I should be able to write all three side ratios, and I should get the same number each time. If you can't write all three side ratios, this theorem is out. If you can write them, it doesn't mean you've got similarity. It just means that you can at least check and see if it's going to work. So if you can't write all three side ratios, you're not going to be able to use side, side, side. If you can write all three side ratios, great, but divide them all out and we're going to make sure they match. All right, so let's take a look at the first example here. Okay, so in this example, I have a side here that's 3 and a side here that's 6. So I have one ratio of 3/6. I have a side pair here that's 4 and a side pair here that's 8. So I have another ratio, 4/8. And I have a side that's 5 and a side that's 10. So my third ratio is 5/10. Now again, they don't look the same initially, but if you reduce them, all three of these ratios are going to reduce to the same number. These all reduce to 1/2. If you're not good at reducing fractions, throw them in the calculator. You will see that all three of those come out to exactly 0.5. They need to be exact, not close, exact. All right, so let's check out our ratios down here on this bottom one. See if we have the same thing. Oh, I should have said this. So because these match, we can say side, 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 congruency. Sorry, skip that part. All right, so let's take a look at these down here. I've got a 30 and a 24. Looks like a 36. I've got a 35 and a 28. And I've got a 32 and a 25. Now, I can reduce these fractions, right? 30/24, those are both divisible by 6. These are both divisible by 7. So if I divide these two by 6, that's 5/4, which is a decimal. If you put that in the calculator, it comes out to 1.25. All right. 35/28, those are both divisible by 7. So that also comes out to 5/4, which again is 1.25. So far, so good. Now 32/25, the only thing 25 is divisible by is 5, and 32 isn't divisible by that. So that fraction isn't reducing, so I'm a little suspicious. If we do 32/25, we get 1.28. Sorry, you have two that match and one that's really close, but close doesn't count. I'm not rounding these. I'm not going to be like, oh, I'll just say they're all 1.3. No. That third one, they used a different scale factor. These are not similar. Bye. Not similar. All right, so third theorem. You got to have two sides and a very special angle. It's side-angle-side congruency, and just like, I said congruency, dang it. It's side-angle-side similarity, and just like congruency, side-angle-side, you have to have the included angle. So that means that if you have this side and this side, you better darn well have the angle where the two of them come together. If you don't have this angle, you don't have the included angle, go look for a third side or go look for another angle, because you can't use side, angle, side. It has to be the included angle. Right. So let's write down. Okay, it says two corresponding sides are proportional. So in other words, I have two pairs of sides where the ratios match. And I have the angle in between. I have the included angle. So again, let's look at a couple examples. In this first one, I've got an 8 and a 6. That reduces to 4/3, which is 1.3 repeating. Okay, I've got a 20 and a 15. Those are both divisible by 5. They also come out to 4/3, which is also 1.3 repeating. So good news, I have two side ratios that match. So if I want to prove congruency, I either need a third side, which I do not have, or an included angle. So let me go over here and grab another color. Notice here, I have this side that's 8 and this side that's 10. The angle that I need is that one right there where they come together. And note, it's got a little tick mark thing, and this one has a little tick mark thing. They didn't tell us how big it is, but they marked them congruent. So these two triangles are similar by side, angle, side, similarity. Don't forget your little tilde. All right, let's take a look down here. This is another one of those little tricksters where they try to get cute and put a triangle inside of another triangle to try to trick us. Well, it's not going to work. So I have this big triangle, BAC, right? Then I have this triangle inside it. So what they did was they drew this line, DE, through the big triangle. And by doing that, they created a smaller triangle inside the big triangle. And that would be triangle DAE. So I have triangle BAC and I have triangle DAE. What I want to point out to you here is because they were cute and tricky, drawing a triangle inside of another triangle, we immediately have an angle here that belongs to both triangles. I have an angle congruency. They're not going to mark it, just like they didn't mark the vertical angles over here. They don't need to mark it. It belongs to both triangles. If it belongs to both triangles, it's the same in both triangles. So I have my angle congruency. I need two pairs of sides and I need to check the ratios. Okay, so check out this on this side of the triangle. My big triangle that goes from B to A has a side of 25. And my little triangle that only goes from D to A is 15. What's that reduce? 5/3? Or 1.6 repeating, right? Yeah, 1.6 repeating if you're doing on a calculator. Okay, on this side, my longer one is 21 and the shorter one is 12. So I have a problem. 21 over 12 doesn't reduce. The only thing, oh wait, yes it does. Oh, mommy. Okay, 21 and 12 are both divisible by 3, so that makes this 7/4. Okay, so just to double check myself, because apparently I forgot my multiplication tables there for a minute. It must be after 9 p.m. Is it after 9 p.m.? Let's see. 25 divided by 12 is, oh my goodness, 25 divided by 15 is 1.6 repeating, as I said, and 21 over 12 is 1.75, which is 7/4. So this is 1.6 repeating, this is 1.75. They don't match. Okay? If they don't match, the fact that they gave you enough information to create those two ratios makes no difference. I have two side ratios that don't match. This is not similar. Okay. So those are your three theorems. You have to have at least two sides. For congruency, you only needed one side. for similarity, you have to